question says, show that. And to show that, the way this happens in real life is you're doing a question and you have no idea how to do it. So do you ever then look at the answer, if you have the answer key, to hope that the answer gives you some sort of hint? So this is sort of what a show that is. You didn't know how to do it. You cheated and looked at the answer key and see that the answer is the natural log of secant x. And at this moment you would be like, well, I would never have guessed that. But it does give you a hint. And the hint that is given to you is that if you had a natural log, you needed to get a 1 over u integral. Does that make sense? So I need some sort of fraction. So probably what I'm going to do is I'm going to change tangent to sine over cos, a simple identity. And then I would make my u equal to the bottom and hope everything else goes away, which it does. Except for a little negative, but we can manipulate that because the derivative of cos is negative sine. And then when we substitute that in, we get 1 over u negative du. And so technically, we would get a negative natural log of cos. And this is also kind of nice because let's say you were smart enough to get to this point, but in the multiple choice question of your AP exam, this wasn't listed. Instead, the natural log of secant x plus c was the answer that was listed in multiple choice. Can you see algebraically how you could go from where we're at right now to making that natural log of secant x? How are they the same? What log law would you like to use?
Coefficient to the...
Yeah, we could take the number out in front, right, and make it an exponent. And if we make it an exponent, a negative 1 would be 1 over cos, which is secant x. Sneaky. So if you have an integral of a trig function, they're often not easy. And they often involve using any one of the identities that you have memorized to play around with. But sometimes you will choose an identity to play around with which helps you absolutely nothing, which is kind of frustrating, but it is still really good. You will actually learn a lot by choosing an identity, playing around with it, and finding out it doesn't work, only to discard it. Try a different identity, play around with it, and maybe it works. Sometimes you'll go back to an identity that you've tried already and like, have I tried this one? And try it again. But it is a strategy for this next section. Okay. This one you almost need the answer to come up with the strategy to make it work. So I want to show that the integral of secant x is actually the natural log of secant x plus tan x. So I need that secant x plus tan x to be my u to be on the bottom. The only thing I can think of changing secant to would be 1 over cos. And if I make my u my cos, my du would have a sign, and I don't have a sign, so I can't use that substitution. But I'm guessing that if you, like, the normal problem solving here is most of you would change this to 1 over cos first, and I'll just tell you that that helps you nothing whatsoever. In fact, the strategy for this one is so, almost feels like cheating. If the answer is natural log of secant x plus tan x, you would need a secant x plus tan x on the bottom. So just put it on the bottom. That seems a little bit like cheating, doesn't it? But if I put it on the bottom, well, that's technically not allowed unless I also put it on the top. All right, this really looks like it is not helpful. Agreed? It just looks like we're making it more complicated. However, if we let the u equal to secant x plus tan x, and you do the derivative of secant x and the derivative of tan x, you will get secant x tan x plus secant squared x, and if you multiply the top out, that's what it is exactly. I sometimes think people did derivatives, found things like this, and then contrived integrals to be like, ooh, isn't that cool that that works? Because then this just simplifies to 1 over u du. Super easy integral. So these first examples, you had the answer. That's not going to be the case on your test or your exam. Other than, I guess, possibly you have the answer when they give you a multiple choice question. They also give you 3 wrong answers. So you could attempt to try each of the answers and see if they work. That is a good multiple choice solving strategy, right? Do any of the 4 answers actually work? If one of them does, it's probably the right answer. But more often you get questions that just start with find an integral. And here you have a bunch of options. Okay, we have an issue here because if you make, like, do you see that this squared means you have a cos 2x inside of something squared? And when you have a function inside of another function, that's usually a chain rule. But if you did a substitution and said u was equal to cos 2x, your derivative would have a sine 2x, well, a negative sine 2x with a times 2. And that doesn't appear in here. So it's problematic to just try normal substitution. But that's probably where I would start if I was problem solving this question. I'd start with normal substitution and go, I see a function inside of another function. I want to try normal substitution. It does not work. Okay? So we're sort of, in real life, we just spent half an hour getting frustrated. So if you can just pretend to be a little frustrated right now, you've just spent half an hour and nothing's working. Oh, there we go. Some of you are good at this and math already. Like, the pre-tests and the quizzes have trained you well, right? So now we have to look, well, where else do I have cos squared? I have sine squared plus cos squared equals 1. My guess is that's where you would go next. Okay? Okay? Just imagine another half an hour, some frustration. It doesn't work. But you would try it. You try changing that to 1 minus sine squared 2x, and then you have still the same problem that you had before, where nothing works. So where else do we have cos squareds in formulas? Well, they appear in the cos 2 alpha formulas. And of the 3 cos 2 alpha formulas, I would probably look at the last one, because it involves just cos squared. So if I had 2 cos squared alpha minus 1, what I'm going to imagine is this part right here, I'm going to plug in a 2x and see what the rest of the formula looks like. And if I was doing this as problem solving, after we remember we're at 1 hour of trying stuff already. We've pretended and were really frustrated, most of you would have given up, I know. But let's say, for whatever reason, you're persevering, right? You're stranded on an island with only this math question. This is like, so you plug in the 2x there, which would make that a 4x, right? And you rearrange to get the co-squared 2x by itself. That would give me a cos 4x plus 1 over 2. Is that helpful? Actually, it is. Because now I no longer have the squared. I could have them both divided by 2 and do those integrals separately. The cos 4x is a simple chain rule where if you did the derivative, you'd multiply by 4. So as a simple integral, if you integrated, you'd also have to divide by 4. And plug back in. And we have our final answer. So integrals involving trig. In your brain, you have to say to yourself, remember to try every single identity I know as a problem-solving strategy. If I haven't tried every single identity I know, I should do that before I officially give up. Are we ready for the next? Ooh. Okay. I'll let you look at it, digest it for a little bit. I'll talk about some of the problem-solving strategies that I sort of use that can help you get started. Okay? Integration by substitution is very helpful for simplifying things, and it usually involves one trig function being inside of another trig function. Or one function, doesn't have to be a trig function, one function being inside of another function. So my first glance of this, I noticed that the 1 plus cos squared x is inside that square root. So I would probably think I'm going to start by making my u that and just see what happens. After the last question, I'm not very hopeful at this moment, because usually what I notice in the last one is my first tries don't work. But I put the u as the 1 plus cos squared because it's the inside function. I look at the du, which is a negative 2 sine x cos x dx. Does that match with what's on the top? Not really, but sort of. And this is why having our identities memorized really well is like, hey, 2 sine x cos x, that's just sine 2x. This actually works as our substitution. But I had to recognize the 2 sine x cos x as sine 2x. This problem with this question is if you don't recognize that identity, you get to this point and give up on this strategy, and now we're attempting another identity, and you've lost the actual right way of doing it. So actually, as another strategy, sometimes I just have a piece of scrap paper and I write down everything that I see. So when I see the sine 2x, I write down, hey, remember that's 2 sine x cos x. Maybe that triggers something while you're working in the question. But after this, life is easy. Add 1 to your exponent and divide. And divided by half is just multiplying by 2. And then you can substitute back in. again, any of these difficult ones, once you get an answer, you can take the derivative and double check, does it simplify to what you got? Because if it does, then you know you've done it right. Take a look at the next. I'll put it up here. I see a secant x, I see a tan x. Just off to the side, what is the derivative of secant x? Do you remember? Secant x, tan x? What is the derivative of tan x? Secant squared x. Okay, so we have a beautiful relationship between tan and secant. They seem to work with each other. What we're going to probably want to do in this question is either make u secant x or u tan x. If we make the u tan x, we would replace out a secant squared. If we make the u secant x, we have to replace out a secant x tan x. So you're going to have to play around it. Sometimes you can be like, maybe your brain says, ooh, I think this one works better. So you're going to try that one first. If it doesn't work, then you're going to try another one. Okay? So what I'm going to do with my equation first is I'm going to be like, let's say I want to use the top one. So then I would have to rearrange my equation so that that secant x tan x shows up. So I broke up the secant x to the exponent of 3/2 to a secant x to an exponent of 1/2 and a secant x to an exponent of 1. And you see that secant x to the 1/2 times secant x to the 1 would give you secant x to the 3/2. Does this clean up nicely if I let u equal secant x and du equals secant x tan x? It does clean up really nice, doesn't it? The other one doesn't really clean up very nice because you would need a secant squared and you only have a secant to the 3/2. So I manipulate my equation knowing what my derivatives are, and then from here everything is super easy. Add 1 to the exponent and divide. But as far as problem solving goes, like when showing you the answers, I'm showing you the right way. But I'm going to tell you when you try these on your own, the right way might not come until your 4th guess. And you might have to try multiple things. And it's not bad to show, like I did in the green down here, a little bit of thinking, how are these things related? Could I get a substitution that makes something go away? All right, we're done the easy ones. Which weren't easy. These ones are sort of another level. Okay, so you have cos to the 5. First of all, that cos x is inside a power of 5. So you would probably think, oh, I should make u cos x, but then your derivative has a sine x and there's no sine x there. So we have a problem. If we make u cos x, we need a sine x as a derivative. Okay? Strategically, right now, this should make no sense, but we'll strategically do this for now. I'm going to break up cos to the 5x as cos to the 4x and cos x. Because I know that if I make u cos x, then I need a derivative of sine x. Or if I made u a sine x, I would need a sine x to have a derivative of cos x. Either way, I want my equation to have both sine and cosine. And what better way to do that than to use our regular identity, that sine squared plus cos squared equals 1. So if I have a cos squared by itself, which I can break up my cos to the 4 to cos squared x, or cos squared x squared. Then I could change one of those cos squared x's, or both of them, which I did here, to 1 minus sine squared x. So I manipulated my equation so it had a sine and a cos. Because if I make my u either sine or cos, then things will disappear nicely. This still doesn't let me know necessarily what I should make u. Should I make u cos x, or should I make u sine x? And again, if you don't know, which I don't expect you to know, the best strategy is to randomly pick one and try, right? And secretly hope you randomly pick the right one, because it'll be less work for you. Or you secretly hope you pick the wrong one, because then you get to do more math. And that's so much fun. It takes longer. You get more fun doing more math because you make more mistakes. This is not a bad thing. Well, you think it's bad, especially when you're trying to get your assignments done and you have limited time because there's like a big Netflix binge happening this weekend that you have to make sure your assignments are done so you can get to that, right? I know. I just started a new series yesterday, and it's not new, but a new season. I'm going to let u equal sine x. Because then this sine x is inside a bunch of stuff. And the cos x dx, that simplifies nicely away. And the other thing I'm going to do, because if I just substitute it in here, you see how you get 1 minus u squared, all squared? I actually FOIL that out. So I get a 1 minus 2u squared plus u to the 4 du, and you integrate all three of those separately, and you would have never have guessed that this seemingly simple integral, how nicely it simplifies, is a terrible original one. And if you did the derivative of that in all of its chain rules and simplified, it'll come out nicely to cos to the 5x. But it's not intuitive. You're learning high-level math. AP Calculus is teaching you high-level math. What you'll find when you learn higher and higher level math is it becomes less and less intuitive. You have to think a lot about it in order for it to make sense. That's just the normal calculus, and now we're doing unintuitive advanced questions on top of that. And there's actually, like, if you do these enough, or if you watch YouTube videos on them, there's, like, this is the strategy you use with an odd power. This is the strategy you'll use if it's an even power. Like there's been people that have grouped them together as different kinds of strategies. I would say if you memorize those strategies, fine, that helps. but at the same time, the problem solving of trying things is actually more helpful for you learning that. So in this one, just to recap the problem solving, I started off by seeing a function inside of a function. And I said, I'm going to try simple substitution, but the derivative of cos is sine. So if I'm going to use any kind of substitution with cos, I need a sine. Same thing is true if I'm going to do any substitution with sine, I need a cos. So that made me think about playing around with this. And since I'm dealing with powers, I was like, well, every time I have a cos squared, I could change it to 1 minus sine squared. But this is where this becomes difficult, because what happens if you thought of doing this first? Right? That still makes cos to the 5x. Right? We still have issues. So it takes a little bit of playing around. Because you might have chosen this, and you could change this cos squared to 1 minus sine squared, and then your u as cos x doesn't get rid of enough stuff. Or u of sine x doesn't get rid of enough stuff. Okay. Again, we see a sine and a cos. So you're going to want to make u one of those. But if you make u sine x, then du would have a cos x, right? And if you made u cos x, then du would have a sine x. Looking at my original equation, beside the dx, is it easier to write a single cos x or a single sine x? Right? What's the problem with the cos x? It's inside a square root. Okay? It's going to be easier if I take one of these signs and steal it. I can put it easily beside the sine x. Because I'm thinking right now of this. When am I going to make my u? Either sine x or cos x. If I make my u cos x, then I'm going to get a negative, which doesn't really matter. I can move it to the other. But I can get sine x dx by itself. So what could I do in this equation then? Well, I can put that sine x with my dx. And then what am I left with? Still a lot of crap, as far as I'm concerned. Still a lot of brain injury about to happen. Doesn't feel like I've gotten very much further. Okay, so if I make my u my cos x, my du can get rid of the purple box, but I still have a problem with sine to the 4. Because it's a sine, and that doesn't get any kind of replacement. So I'm also going to think about that sine to the 4, I can write as sine squared squared, which I can change to 1 minus cos squared. I'm going to make my u cos x, then I want to get as much as I can with cos x with the rest of it, and only have the sine x stuck with my dx. You could either do the substitution here, or you could actually, yeah, I like it here. If we do the substitution here, I've got 1 minus u squared, all squared, and then u to the half. This I can't integrate easily unless I expand it all out and distribute. And then you can substitute back in. Look at that integral. Oh my goodness. Those last parts, that's when life gets easy again. But we still had to expand things to get it into a form we could integrate. So again, to recap a little bit here, you have cos x inside of a square root, so it's inside a function. You have sine x inside a power of 5. So they're both inside functions. So initially, I'm thinking I'm going to make u either sine x or cos x. I don't know which one. But I know that if I make u one of them, I'm going to, when I take the derivative, have to have something go with the dx. So I looked at my equation and which was easier to go with the dx, a cos x or a sine x. And it looked like the sine x was easier. So I'm going to try that as my problem solving strategy first. And anytime you have an even power, you could break them down so that you can replace something eventually with a sine squared or a cos squared x. And expanded it all, and it worked out. Even though the final answer is very complicated looking. Like who would have guessed that you could do the derivative of that and simplify it? The next two have tans and secants. So I'm going to just pull up a previous screen where I have the tan and secant. And you're going to have to decide and try. And take out scrap paper if you want. You don't want to write your own notes. You can grab scrap paper from the bin here or take out your own loose leaf. Make a decision. Try one. Are you going to make u equal to secant x or u equal to tan x in these last two? And also, I'm going to, in addition to the derivatives that you had, maybe you should write down that tan squared x plus 1 is secant squared x. That's an identity. That might be helpful. So write down tan squared x plus 1 is secant squared x. I'll put up these derivatives there for you so you don't have to copy them down again. And you have to make a decision if you can play around with it to get, should you make u equals secant x or u equals tan x? I'll give you the hint on the first one. If you didn't get the first one, the hint is you should make u secant x. So see how you can now play around with this to make it doable after that. So if you make u secant x, then one of the tan x's and one of the secant x's has to go with the dx. I'll write that out. This tan x, highlighter, oh, so much fun. I love highlighters. Green. This tan x and this secant x are going to go with the dx, leaving me still with a tan squared and a secant cubed. How is that helpful? The rest of this answer. So if you did do the other one, you could manipulate. But here, if I did it this way, this part, the green part, is going to go away. I can change tan squared to secant squared minus 1, which if I distribute, maybe it looks a little bit simpler than the tan one.
Oh, yeah.
But the tan one would work in this situation. All right, look at the last one. If you make your tan x, then du would be secant squared. So I have to break things up so that I have secant squared dx. Okay. Tan x is going to get replaced with a u, so I change my secant to the 4 to tan squared x plus 1, all squared, because that's secant squared squared. Distribute. First I would square this, then I would distribute my u squared after that. And simplify. Is that our last? Yes, that's our last one for Trig. I'll end the video here.